let me go through this exam. I think I put your scores up and I'll hand it back next time. The problems are based entirely on the homework and what we discussed in class. So the first one is a Gaussian random voltage is a mean of 3 and a variance of 6. What is the probability of the voltage being greater than 0? And I'll put all this stuff up, by the way. Greater than 0. And so it's probability of V less than 0. Here, that table I put in the back, you can do two things. You can use your calculators, you can use the table. It's the probability of voltage being greater than 0. By the way, most people got this right. And it's 0.8897, and it's just looked up. You have to take the actual value minus the mean divided by the standard deviation. Standard deviation would be square root of 6, and you'll get this value. I mean, were there any questions about this, by the way? It doesn't matter if you use Q tables or characteristics tables as long as you know how to use them. Anything at all? Most people had no problem with this. Next, what is the probability of voltage greater than 1 and less than 3? It's really integrating the Gaussian density function between these two values, and you can use tables. You can take the probability of the voltage being less than 0, then subtract from that the probability of the voltage being greater than 3, and you'll get it. But you can do it many different ways, and you'll get 0.3897. Finally, what is the probability of voltage being greater than 6? And the only thing you could use the tables, or you could use just the Q function to do this, or you could use 1 minus the characteristic function to get the same value. And the only thing you're doing here is just showing me, how to use the tables or use your calculators. You all with me on this? By the way, I didn't break this out to see the percentage of people got problem 1 right, 2 right, and 3 right, but I'd say 90%, 95% of the people got this one right. And that's why I'm going through it kind of fast. Finally, what is the probability of voltage being greater than 6? And that's simply going to be, if you're using a Q table, it's 6 minus 3 over square root of 6, or it's 1 minus the characteristic function with the argument of 6 minus 3 over square root of 6. Now, the next part, there were a few people that messed this up, but it wasn't meant to be tricky. This is a Gaussian probability function. And what is the third central moment? Remember, a central moment takes the value of the Gaussian, subtracts the mean from it, and then it does the integration. Well, if you subtract the mean from that, you're really integrating below and above, and it will be 0 when you do the moments, because you'll multiply by x. So it's 0 for the third central moment. And what is the third moment? And that's the one where you're basically going to go ahead and you'll take, you can do it this way, the way I've shown you, where it's 3 times sigma squared. So this is really this 9 times the standard deviation plus the mean minus 27 times the mean plus 27. And you're going to get 81 no matter how you do it. But the third central moment, you remember that formula for the third central moment for a Gaussian? It's really going to be 1 times 3 times n, and then it's going to be times the standard deviation to that power, and it would be third power. It's 81. I mean, sorry, that's for even. This is the third central. This is where you're going to end up using this form of it when you do the expansion. Were there any questions about this? This was from your last, I think, quiz. I actually asked this. You all good with this, guys? Mm-hmm. Let me go to the next part. So this is the one I want to talk about. So here, the amount of distilled water dispensed by a machine. By the way, I actually, I believe when I sent out that pre-test information, I asked you to read through some pages. This was right off the page. I didn't change anything. Did anybody recognize this one? I'm curious.
I did, I think.
It is exactly the same. No modification at all. So if you did the pre-exam work, you should have seen this one coming, and it was straightforward. You can use the tables in the back, or you can use your calculators. A lot of people chose to use their calculators, and if you know what you're doing, it's not a problem. So to determine the container size, we need to find the value of C such that overflow occurs only 0.5% of the time. That means it doesn't overflow 1 minus that percentage, and this is really 0.005. So it's 1 minus 0.005 or 0.995% of the time it won't, since the amount of distilled water dispensed in the machine is normally distributed. With a mean of 64 and a standard deviation S, we can use a standard probability normal distribution. That's at the back of the test here. Well, unfortunately, the tables didn't show here, but I can pull them up in a second. Let me see if I can actually get these tables. I know I have them. All right, can you see these tables right here?
Mm-hmm. Yes.
Okay. These are given on the test, and so this is the cumulative probability density. It's really the characteristic function we talk about. And if you take a look at this, these are the negative values. Then for the positive values, they're behind here. And basically, you're going to be looking for a 0.995, and I think it comes right in here. Either one of these two will do it. Can you all see that cursor, by the way, guys?
Yeah, we can see it.
All right. Now, see, it's 0.9949 to 0.9951 right here. And so it's 2.5. And then if you look at the, comes down to 0.7 or 0.8. So 2.507 or 08. And when you do that, let me get down here. You have to take 64 ounces. Yeah, this is the Z value. X minus U over sigma is going to be the Z value. And that's shown here. Let me just look here. 2.58 is about right for this one if you look in the tables. And that means 2.58 is C over 64 divided by 0.78, which is the standard deviation, and gives me about 66.01. 66 got you that. A lot of people went the other way. Instead of adding this difference, they subtracted and they got a value less than 64. But this was meant to be just a straightforward problem of using the tables or your calculators. And a lot of people, I didn't break it down, but I'd say about probably 65% of the people use their calculators to do this problem. Were there any questions about this one? This is just using the tables or your calculators and knowing how to do it. Y'all good with that? Next, this is the dinner party with wine. I was going to make this a little more complicated, but I figured I'll make it simple. A friend of ours is giving a dinner party. Her current wine supply includes 5 bottles of Zinfandel, 4 Merlot, 6 of Cabernet, all from different ones. She wants to serve 3 bottles. Now, this is a template problem. You had a quiz on this. We discussed it, and there's nothing that was meant to be tricky about this. She wants to serve 3 bottles of Zinfandel, and serving order is important. How many? This is the combinational thing. So, permutation thing. And so 3 bottles and serving order is important. So with Zinfandel, you got 5 bottles. She want to know every possible way you can serve 3 bottles of that. And that's going to be the permutations here of 3, 5, and it's 60. I'd say 95%, maybe 98% of the class got this right. The next one is, if 9 bottles are randomly selected, how many ways are there to obtain 3 bottles of each? Okay, that's the combinational stuff right here of 915, and it comes out to this number. Y'all seeing this? Okay, it's meant to be very straightforward. If you know what you're doing, there was really probably no hesitation. You're just going to the formulas and using it. The only thing I think may have been difficult, some calculators may not have done factorial, but I've never seen a calculator that doesn't do that. I think they all do it. All right, finally, part C. If 9 bottles are randomly selected, how many ways are there to obtain 3 bottles of each variety? And here, now you have to do, remember, this is going to be multiplicative. It's combinations of 3, 5, then combinations of 3, 4, and combinations of 3, 6. And it is multiplied because if you think about this, if you just had one or the other, you might say 2 possibilities, but you got all these 1,000 other possibilities. It still means it would be 2 times those number of possibilities because the front one could be changed. And I'm not saying this very well, but hope you get this. So this is multiplicative every time. So there's 800 ways or 800 different combinations. Finally, part D, of 9 bottles are randomly selected, what is the probability that will result in 3 bottles of each? And that's just K, the prior one, over the combination of 915. And it comes out to this value. I don't know, but I think some people punched into their calculator wrong right here. I'm not really sure why you didn't get that right, but it's hard for me to tell because I just see the answer and you might get this one right and you get this one wrong. And I don't know what you did wrong because there wasn't enough information. finally, the last part, E, if 4 bottles are randomly selected, what's the probability that all of them are the same variety? So it's really, this is one of those crazy combinational things where if 4 bottles are selected from 15, this is the number of combinations possible. Then you have to find 4 of 4, and that's 1, and then 4 of 5 plus 4 of 6, and it comes out to this value. And this literally was, I used the template of the prior one to create this one. And if you learn from your mistakes last time, this should have been fairly straightforward. Were there any questions about this? I'm going to post all this stuff up there. All right, any questions at all? I'm going to breeze through this thing. Finally, the last one, or actually, this is the one that I'd say some people had problems with, and other people's just whipped right through it. And I wasn't sure what the problem was. So this is a density function, and it's a joint density. Now, the one thing you had to realize is if you integrate a joint density function over the region it exists, you have to get 1. It doesn't matter if you do it numerically or if you do it by parts, but you have to get 1. So the value of A that'll make that 1 is when you integrate this from dx dy from 0 to infinity in x and y. And you can do it by integration by parts. And some people did. Or you can do it numerically if you want, but you have to do it, and you're going to get a value of A is 6. And I don't know. Yeah, here it is. A is 6 right here. When you do it, if you want me to do it by parts, I'll do it. But it's a straightforward integration. This is the one integration we actually talked about in class. Your calculators do it symbolically. You can do it. You don't have to. I did it longhand. And this is the density is 0 for less than 0. So to get A, you have to integrate this dx dy from 0 to infinity in both cases, set it equal to 1, and A comes out to be 6. Because when you integrate each of these, you're going to get 1/2 for the first dx integral. You're going to get 1/3 for the dy integral from 0 to infinity. And that means it's going to be 1/2 times 1/3 is 1/6 times A equals 1, or A has to be 6. After you get that, to find the probability of x being less than 1/2 and y being less than 1/4, now that you have A, it's simply integrating this thing. If you want me to, I'll do the integration, but straightforward. You're integrating this where there's a 6 there from 0 to 1/2 and from 0 to 1/4 y. And you get the value here is 0.3335. You all with me on this, class? I'll be happy to do these integrals if you want me to, but they're straightforward. There's really no trick to it. Then the expected value. Oh, sorry, the first one wasn't an integration by parts, pardon me, but for the 6, it's not integration by parts. Here, it's integration by parts. If you want the expected value of x, y, you have to multiply this by x and then by y and do the integrations. Now you get x times e of minus 2x, and then it's times y times e of minus 3y, and that is an integration by parts, and you'll get this value if you do it correctly, but your calculators, a lot of people just did it on their calculators and they got that value. Some did it long-handed. Y'all with me on this, class? I did not try to make this a difficult test. It's just making sure people know how to do the problems that we talked about, especially the ones that were in prior quizzes and stuff. I want to just mention one thing. The one thing that more people miss than anything is right here. This is a real high average, even with the zeros for people that didn't take it. I think it's a 77%. I can check that. Very high average, a lot of really high grades, like perfect. But this is the one problem, and it was because I think they messed up that integration by parts. It's the only thing I could figure, because it seemed like you knew what you were doing, and then you messed up the integration by parts, or you typed it in your calculator wrong. I'm really not sure. Are you all with me on this, guys? Well, that was painless and quick. I want to get to this Q camera thing. So I'm using the old book right here, the prior one. And when we get back in class, I'll probably be using the new book for some of this stuff. But since we got this here, I want to go through some of this stuff. I didn't give you anything out of section 3.2 with conditional probability. So we were talking about this last time. I don't know why that isn't more lit. But this is on page 124. I don't know how well you can see that, but the resolution on this camera is pretty good. Not really good, but you can see it. By the way, you see where that problem came from? Right there. It's right out of the book. So if you were doing the homework and did that, what I asked you to, every problem, just about every problem on that test, you actually had before. Maybe I changed some values, but that was it. I didn't do anything tricky, nothing tricky at all. Okay, back to this thing. So if we talk about probability, density functions, and conditional probability, there's some reading on page 125 here that will that you can do if you want, but I'm just going to make mention of something. What it comes down to, and the key, in my opinion, is right here. That if you have a density function, a joint density function, and you say that there's the probability of one or the other having a certain value, and you want, therefore, the probability density function and then the probability of the other variable, first the density function, you take the joint density function divided by f of x, and the way you always get this, the single density, is just integrate out for y here. So if you got f of xy, and I hope you can hear me, and you want f of x only, you integrate this thing with respect to y over all possible values. And you get this, that's a joint density function. In the same manner, if you can take a look at this, if you wanted f of x given y, the only difference is now the denominator is f of y. And it's straight. There's nothing tricky about this. And if you want to see the actual proof of this is here. I didn't do this on the board. I may next time just to show you. But it really boils down to an aerial thing where if you take a look at a joint density function and you look at they call it a heat map, really a surface map where you have x, y, and then f of xy is the surface area. Anytime you're talking about the probability of a certain event for like y less than or equal to some value, it automatically limits the region of the actual f of xy or f of xy. Then when you say you want the probability of f of x being any of these values, you have to integrate over the remaining area, the surface area that's limited because you limit one of the two variables and set that equal to 1, because it has to be equal to 1 to calculate the constant that would be in front of the f of xy given y distribution. I'll show you, but this is what's going to come down to always. The normalization is taken care of when you do this. So in his book, he's got, he shows you some information here. And one of the things we might as well just talk about for a second. I don't want to really spend a whole lot of time talking right here about some things, but if you have joint density functions, and I'm going to write here for the first time, but if you have joint density functions, like so, if you have f of x comma y, and it's anything at all. If you think about this, this is what I'm trying to show you. If this is x and y, f of xy is a surface map, really. It's something, it's the height coming out of there. So if you want like the probability of x being less than 5, given that y equal 5. Now, what you end up doing is you're saying y is 5 here. Y'all follow me on what I'm trying to show you pictorially? Y is set in concrete. It's got a value of 5. Now that means if you integrate this f of xy from here to here, whatever value it has, that has to be equal to 1 over all possible values. Does this make sense? Just think about it. You're going to have f of xy. Now you're going to have f of x comma 5 here. Now, when you integrate that thing over all possible values, it has to equal 1, right? And if it equals 1, you would effectively get a coefficient in front of here. You would have to multiply it by, so you could then go ahead and estimate if you want the probability of x between like 2 and 5, given y is 5, you would integrate it over that limited range to get it. But what happens is what you can actually do is say if you want f of x given y here, but here you can, the normalization is taken care of when you actually do this. You get f of x comma y divided by f. Now it's going to be f y of y And this fy of y is simply the integral of f of x comma y dx, and it would be over the range, whatever the range is, from minus infinity to infinity. It would take care of it. And that's really it in a nutshell, how you get this. Might as well do this exercise. So I'm going to just show you this. They say they have f of xy is kx plus 2y from 0 to 1, 0 to 1, 0 elsewhere. And this is exercise 3.21. Do you all have access to the text, or if you want to pull them up? So if we're do this, just talk. Let's go through this, and I'll do it simply as possible. So I have f of x comma y equal, and this is kx plus 2y, and this is for 0 greater than x comma y, less than 1 on both cases, and 0 else. And then they ask first and let's make sure everybody gets this, what is k? And anybody want to tell me? I don't mean to insult you, but I just want some coffee. So everybody got an idea? I think you all know. What are we going to do? We're going to integrate the function over the range it exists and set it equal to 1, right? That's it in a nutshell, right? And you all know that. So I'm going to say 1 is therefore equal to the integral of k, and this is going to be x plus 2y, and it's going to be dx dy, and it's a double integral from 0 to 1, 0 to 1. I have 1 equal k, and then when I integrate x dx, I'm going to get x squared over 2, and I'm evaluating that from 0 to 1, so that's going to be 1/2, right? That's the first integration. Then when I integrate 2y dx, I get 2yx from 0 to 1 is just 2y. And I have that. Then I have to do the dy integration from 0 to 1. Can you all follow me what I'm doing, by the way? I'm not trying to make it harder than it really is. So if you do that, you got 1 equal to k here. And now I have 1/2 dy is 1/2 y from 0 to 1 is just 1/2, plus, and I have 2y dy would be 2y squared over 2 from 0 to 1 is just plus 1. So that means 3/2 k is 1, or k is equal to 2/3. And that's the middle answer, but it's correct. Does everybody follow me on this, class? All right, next, he asked for the conditional probability that x is greater than 1/2 given y is 1/2. All right, so first thing I'm going to do is to get the conditional probability density function. All right, so now we want the probability, part B, that x is greater than 1/2 given y equals 1/2. So what I'm going to get is f of x given y. And I'll just restate it. That's f of x comma y over f of y of y. So to get f of y, I have to take the joint density function, which is f of xy, and I have to integrate that from 0 to 1, and that's going to be k, which is 2/3, times x plus 2y, and I have to integrate that dx. So if I do that, I get 2/3, and then I integrate x dx is x squared over 2 from 0 to 1 is 1/2, plus, and I integrate 2y dx, you get 2yx from 0 to 1 is just 2y. Right here. So that's my f of y. Put it right here. So you all can see fy of y is equal to 2/3 times 1/2 plus 2y. Finally, I get my f of x given y is f of xy, which is 2/3. And then it's going to be x plus 2y. I'm just taking this, I'm taking f of x, y divided by fy of y, divided by fy of y, and that's 2/3 divided by 1/2 plus 2y. So the 2/3 cancels. And then I know that y is equal to 1/2. So that means this. Right here, since y is equal to 1/2, I get x plus 1 over, and that's 1/2, that's 1 plus 1. So it's x plus 1 should be the dense, it should be f of x given y, where y set equal to 1/2. Do you all agree with that, class? The next thing I'm going to do is, since that's the density function, they want to know the conditional probability x is greater than 1/2. So to do that, if we want the probability of x greater than 1/2, given y equals 1/2, that's simply going to integrate this. So it's the integral of x plus 1 dx, and it's from 1/2 to 1. Does everybody agree with this, by the way? It's a plug and chuck. If I do this, let me see if I can.
What'd you say the denominator would be again? It'd be 1/2 plus 1, correct?
Well, if you have, do you all agree that 2/3 cancel, Michael? Can you see how the 2/3 is going to cancel?
Yes.
And this is, the remainder is 1/2 plus 2y, but y is 1/2, right? Oh, I'm sorry. You know what? If that, yeah, that's, if this is, sorry, if this is 1/2, this is 1.5. I'm bad about that. So that really would be divided by 3/2, right? Or times 2/3. I'm sorry. I'm glad you caught me on that. Y'all with me? I apologize. I thought they made it easy, but so there is a 2/3 here, or 3/2 there, which will turn into 2/3. Now, let me move this here. So that means I have 2/3 here. And now, and that's the bottom one. Then when I integrate x dx, I get x squared over 2. And I'm going to go ahead and put that down so I don't make another mistake. From 1/2 to 1. Plus, and I get 1 dx, which is just x from 1/2 to 1 is 1/2. Can you all follow me on there? Catch what I'm doing. I literally showed the limits of integration in there, and I showed what's going to happen. Okay. Now evaluate it. I'm going to go this way to evaluate. So I have 2/3. And this is going to be, I'm going to put the 1/2 first right here. Plus, now when I integrate this, well, 1, this should be over 2. I don't know how I forgot that. So when I have 1, so it'd be 1/2 times 1 minus 1/4 or 3/4. So it's plus 1/2 times 3/4. And that's 2/3. And this is going to be, what is this going to be? 7/8, right? And what does that come down to? 7/8, so that's 1/4. So 7/12. And that's the last answer in the book. Do you all see that, class? All right, that's right here, 7/12. Y'all, I mean, y'all follow what I'm doing and why I'm doing it. Next, finally, I'm going to have to turn the page on this. The last thing he asked for is, the next thing he asked for is, I'm going to get my hand out right. So they want the conditional probability that y is less than or equal to 1/2, given that x is 1/2. So I'll just put x equal 1/2. For this one, first thing I'm going to do is get f of y given x. And that's, again, f of x, y, right? And then it's going to be over fx of x. Take a second. Do you all agree with that? Everybody? So for that one, we got f of x, y, and I'll put it here. That's 2/3 of x plus 2y. And this is x, y greater than 0, less than 1, and 0 else. Now we need f of x. So fx of x is going to be this thing. It's 2/3. I'm going to take that cost out front. Then I have to integrate x plus 2y dy from 0 to 1. Everybody agree with that, by the way? All right. If I do that, I end up getting 2/3. X dy is just xy. For y from 0 to 1, it's just going to be x, right? And then you're going to have 2y dy integrated as y squared over 2 times 2 is just going to be y squared. Evaluated from 0 to 1 is 1. Y'all agree with this so far? We're going to put in there, it's this is x is 1/2 is the definition. So if x is 1/2, if we put half of x equal 1/2 here, you're going to get 2/3 and x is a half. So I have 1/2 plus 1. So it's 2/3 right here times 3/2, right? That's 1, which is nice. So now we have f of x given y equal, or sorry, f of y given x equal 1/2 is simply going to be equal to, really it's f of x1, it's just 2/3. 2/3 x is 1/2, so it's 1/2 plus 2y. And what does that come down to? Let's see. That's 1/3 plus 2/3 y is going to be my f of y given x. And then they want what is the conditional probability that y is less than or equal to 1/2. So, I mean, are you all with me up to this point, guys? Okay. And then finally, the probability that y is less than 1/2 or equal to 1/2 given x equals 1/2 will be equal to the integral from 0 to 1/2 of 1/3 plus 2/3 y dy, and that comes out to be 1/3, and here you're going to have integral of dy times 1 is y from 0 to 1/2 is 1/2 plus, and then it's 2/3 integral of y dy is y squared over 2, and when it's going to be 1/2 squared times 1/2 because it's going to be 2/3, then y dy is y squared over 2. So that's the 1/2 here, and y goes from 0 to 1/2. So what does that come out to be? So I have 1/6 here plus, cancel that, and I have 1 over, that's 4/12 plus 1/12. That's equal to 3/12 or 1. Did I do that right? Let's see here. That's 1/6, right? I'm getting 1/4. Yes.
I also got 1/4.
Well, the book has 1/3, unless.
I have a question. When
Yeah.
back up, shouldn't it be 4/3 y? Back up on when you multiplied the 2/3 on that line where you crossed out f of x given y, you multiplied 2/3 times 1/2 plus 2y. Shouldn't it be 1/3 plus 4/3 y?
Might be right. Let's see. That's 1/3 up here. 2/3 times that's 4/3. You were absolutely right. That's on me.
Right.
Thank you very much.
Yeah, I calculated that. That should give you 1/3, I think.
Yeah, that's what I got.
So it'll give you 1/6 plus 4/24 instead of 2/24.
Oh,
You
that
should
is 1/3. That's on me. I'm sorry about that. I should be more attentive here. I made a mistake. You're right. You're absolutely right, guys. Y'all with me on this? As far as the method, at least, right? The only thing you're doing is applying the formula and doing the integrations. Now, I'm going to say one other thing too, about this. That's a straightforward example of just conditional probability in a nutshell on how to do it. There's some things in here that get a little confusing. I want to just mention this. So I'd rather do this on a board. But if you take a look, I don't know if he has this one. I'm going to show you this, and I hope you can all see this. Can you see here how he has f of y given x? Let me see if I can blow that up a little. Okay, if you look at equation 315, and I hope you can see it where my fingers point. And then, well, actually, we can go up here. So f of x, technically it's f of x of y dy, but you can replace f of xy. If you look at this, sorry, look at 314 for 1 second. You see f of y given x is now he puts it as f of x over y. That's really f, the top one is f of xy, but it is the same thing. And I better stop for a second and just explain what I'm doing. So I'm coming back to here. Remember, f of x given y is f of xy over f, just f of y. So if I multiply by f of y, I get f of x comma y is f of x given y times the density function of just f of y here. Can you all follow me on this? You'll see where the argument's going in a second. With me? This is just another way of writing f of xy is f of x given y times f of y. It's mathematically true. Are you with me on this? You'll see why I'm saying it in 1 second. Now I'm going to flip the page. I could rewrite this, but I think it's maybe a little easier just to look here. Now, if you look here and come here, you can see f of y given x times f of x, just f of x of x. The same things as f of x given y times f of y. So really, the way I think about this, if you look at f of y given x times the density function of x, it's got to be equal to f of x given y times the density function of y. There's different ways to say this thing, but it means the conditional probability of y given x or x given y can be gotten by just rearranging these things. So here's why it's important. If you look here and here, instead of integrating f of xy, they replace that with f of x given y times f of y, or f of y given x times f of x. And the reason they do this is this may be something that's observable, whereas the density function they'd like f of xy, might be non-observable. And I'll try to take you through this without making it too confusing. I'll do some problems, but I'm just asking you to bear with me on this, because I think it's going to be easier just to look here and see it. So now we get to the situation that this is a very common situation. We have something we're measuring. It could be a voltage, it doesn't matter, but there is noise. Now that's true for just about any real world measurement. There's noise. And noise, if it's caused by, if it's standard noise, thermal noise, things like this, that has to do with some, you might say, inherent natural, it could be the thermal noise or anything like that, shot noise. The density function for the noise will be well known. It'll probably be Gaussian, almost always. But if you say what's observable is y, now here he's taking, I suppose, a signal x of t is perturbed by additive noise. That's a voltage, you can assume, and that the sum of the two y of t is the only quantity that can be observed. So that's this. Hence, at some instance, there are 3 random variables. Now, the idea is this. I know the statistics of n. I'll know it's random noise. And now I want to find the probability of X having a certain value given Y is observed. This is the idea in this. Y'all follow me on this? We can measure Y, so we can measure, we want to know what the likelihood is that X has a certain value. And remember that noise is going to be Gaussian distributed. So this becomes probabilistic. So it's desired to find the conditional probability that of function X given that Y is observed. Therefore, we want X given Y. And we want the most probable value of X. Do you remember how we always got the most probable value of any function, class? What did we do? You can unmute yourself.
Derivative set equal to 0.
Yeah, that's right. We take the derivative of the mathematical function, right, and set it equal to 0, then solve for the value of X in this case that would make it 0, which would be the peak value. We assume the derivative at the peak is 0. Goes up, right? It's going to go up, then it goes down. Well, at the peak, the derivative with or the slope of that is 0. So we're going to observe, we're going to try to estimate the true value of X. Now, this is Bayes' theorem in a nutshell. But if X is given as implied by f of yx, then the only now here's the deal. This is the formula he's talking about right here. So we are observing and we have a value of Y. So we've got the value of Y and we're trying to estimate the value of X. And if you look at this, it says, now remember this statement right here, Y is X plus N. If Y is observed, or if we want like X and Y is observed, or if we observe X, maybe I should say it this way, which is impossible. If we knew X, then the only randomness in Y would be the noise. And this is what he's going to say. So he says f of X given Y, and this is what we were talking about earlier, is f of Y given X times f of X. And this is the same thing as f of X comma Y divided by f of Y. But if X is given as implied by f of Y given X, then the only randomness is the noise. So if we have X given here, the only randomness in Y is the noise. And what he's going to say is that makes this function. If X is given, Y is going to have the same statistical variance as the noise. And then you have to, what you end up doing is this. If you look here, you have Y equals X plus N. So if X is given and you want Y, well, you got the density function for the noise. So you get the density function for Y, you're just going to add on the mean value of X or the observed value of X. So here he's going to say f of X or f of Y given X is f of the noise Y, but now the noise, instead of just having the N, now you have Y minus X because X is assumed observed and you have this, assuming that this occurs. This is it's a little confusing, but it should make sense if you assume you know the value of X, then the noise is the only thing that exists with randomness. You know the statistics for Y. You just have to skew the value of the mean for the noise. Does this make sense to everybody? Until you see it done in problems, it's a little confusing. So we want to find this though. So now we say we have f of n of y of x times f of x. That's this. Divided by f of y. This is the same thing as f of x comma y. We've got that. But remember, we want f of y, right? Now check out over here. Well, this is f of x comma y. And you remember, I told you, you have to integrate that over dx to get f of y. Do y'all remember that? I want you to make sure you see it. It gets a little confusing until you do some problems. Are you with me on this, guys? All right. Well, if I go ahead and integrate this as such, that's a noise, right? You're going to end up getting, let me put it to you this way. Here's what he's going to say in a nutshell. He's going to say this right here is a constant, basically. So if you wanted the most probable value of x given y, you're really going to take this thing right here and take a derivative with respect to x and set it equal to 0. Do y'all hear me on top? That would be the most probable value. So you're going to take this right here, the upper part, the numerator, take a derivative with respect to x, set it equal 0. This down here is just going to be a constant value because y is known. Do y'all follow me? F of y here, y will be known. It's observed. So the most probable value of x, you take a derivative of that. I'll admit, until you see some of this stuff work, it's a little confusing. So he gives you an example right here. F of x is b times the exponential of minus b of x. I want to work some more problems in class for sure on Wednesday with this. Now remember, he's given you the statistics of x. So in other words, if it was a voltage, we'd have to know something about the actual statistics of that, or the probability density function for this thing to work. And most voltages, believe it or not, most man-made voltage sources, the statistics are very well known. As a matter of fact, they may be something where the actual standard deviation of this is so small, it's insignificant, which is nice. So then I turn in the page and I'll do some of these. When I take a look at the noise, it says, suppose that there's noise. Oh boy. He says a space probe with high energy particles, it's converted to a voltage. It doesn't, all this doesn't matter. What he's saying is we have noise, and the noise has a random distribution or Gaussian distribution with a zero mean. Now, y'all can, y'all can see this. This is the equation he's given. That's just the standard Gaussian function, and it's got a zero mean. Y'all with me on this? All right, now, the marginal density function of y, which appears in the denominator of 317. I should write all this down, but I'm trying to save on time. So here it is, right? Remember, we know f of x. If you look here, we know this. He's given it. We know this Fn is just Gaussian distributed. You all with me on this? We know this. We're going to substitute in for n y minus x. So right here, what he does is exactly what I'm showing you. First, he's going to get f of y here. And the way he gets it is by taking this and doing setting up the integral. So he's saying this right here is f of y, and it's really the integral of f of x comma y, which is this. And he's doing the integration. Now, just bear with me on this one. So he's got this crazy thing. And you'll notice there's an e to the minus bx, then there's an x inside this thing, and it's a dx. You've got to expand this thing. You get y squared minus 2yx plus x squared with a minus sign in front. You have to break it up if you want to do this. But at the end of the day, you get this. That's our q function. Do you remember q in the back of the book is the integral of that Gaussian from that point, whatever point it is, from a to infinity, and a would be the actual value y minus the mean value over the standard deviation. This is what he's showing you right here. Now, I don't expect you to have to do complicated integrals like this, but you have to appreciate why he's doing it. Are you with me, class? This is the key part, and you should like underscore this or do something to make sure you understand. It should be noted, if one is interested in locating only the maximum or the most probable, is not necessary to evaluate f of y. And everybody said amen. And then that means the only thing you have to do, this is f of x given y, remember. Okay, he does that. And here we go. So remember, the only thing, you don't have to evaluate this f of y business. The only thing you have to do is find the maximum of this. Now, if you look at this right here, there's two ways to do it. You see how right here, there's an exponential, and the argument inside the exponential will be, this will be a maximum when it's e to the 0 if it can't have positive values. Do you all agree with that, class? If you have e to the minus x squared, the value of x that makes that a maximum is x equals 0. So you just set that equal to 0, and in doing so, you can forget about the 2 sigma squared here. When you set that equal to 0, you get this right here. And that means the most probable value of x will be this. And it's just rearranging terms, taking 2 times y minus b times sigma squared to this side and dividing by 2, and it would be x equals that. Now that's the most probable value. Can you all follow me on at least the reasoning behind this? Now, if you have some other kind of functional form, then you have to take a derivative. But if everything boils down to an exponential inside there and you want to max it, and it's got a negative sign here, all this stuff strict positive, then you have to go ahead and just set it equal to 0. That's how he does it. He shows you some things that are important to at least appreciate. He's showing you he's showing the density function f of x given y. And he's saying when certain conditions occur, if y is less than this value, which is going to be negative, all right, this is going to be a positive value, then f of xy has a peak right at 0. I'm going to have to start looking over here. But if y is, I'm sorry, for the case of y greater than this, then these statistics get a little skewed and you end up having to solve for the derivative. Now, I'm going to try to make sense of this before we leave today. I want to just discuss the next exercise and try to explain why certain things occur if I can. So the next exercise, and I'm going to unzoom it for this one if I can. Now I'm doing this problem, 3-2.2. This is a good problem. And I'll tell you, mathematically, I'm not going to stress you with crazy integrations, but a random signal x is uniformly distributed between 10 and 20. This is perfect. And observed in the presence of Gaussian noise n, having a 0 mean and a standard deviation of 5. So let me first get this one. So we got a random signal x is observed and distributed between 0 and 10. So we got f of x, and it looks like this. I'm sorry, from 10 to 20, from 10 to 20. And this is the PDF f of x, and it's got to have a value of 1/10 here for the peak value because it's going from 0 to 10. This is x, and it's a voltage, and it is observed in the presence of Gaussian noise. So now we're going to have y here is going to be really x plus the noise. Y'all with me on this? And the noise, f of n has the value 1 over the square root of 2 pi sigma the noise exp. It's got a 0 mean minus n squared over 2 sigma squared. I'm just writing this down so everybody knows. The noise has got a Gaussian distribution. It's got a standard deviation of 5. So sigma equals 5, sigma squared equals 25. Y'all with me on this, class? Just restating it and putting it down. Then he goes on and he says, if the observed value of the signal plus noise is 5, so now part A, we have y here equal 5. It's given. I call it y. Find the best estimate of the signal amplitude. So they want us to estimate x. Y'all hear me on this, class? All right, now here's the beauty about this. So if I look at this, I've got y is equal to noise plus signal x. I see y at 5. Now look up here for a second. I've observed y at 5, and I want the most probable value of x. Let me try to explain this. So I know that the noise here is Gaussian, right? So whatever value of x is, when I add the noise to it, it really, since y is observed, right, for this thing, and it's uniformly distributed, if I add noise to this, there'll be some, let me put it this way, x would be equal to y minus the noise, right? In terms of what it's equal to. And we want the observed value of x. Well, the noise is Gaussian. This is observed. What this is telling me, it takes that Gaussian distribution and it skews it down by 5. So if you think about 5 here, I'll try to redraw that so everybody can appreciate this. I hope you can appreciate this, but I'm trying to make it easy. Here's 10, here's 20, and my observation is 5 for y. That means if you think about the Gaussian distribution on the noise right here, added to the observed value of y, here's the location. Really, this would be about the statistics you can see the most likely value would be 10. Do y'all see that right there, class? It has to be. Right? We can prove this, but frankly, that's the value that's closest to this. That's part A. I'll do more of this in class. I'm trying to finish this example. Part B, he says, if the observed value, so it would be 10 for this one. So part A's answer would be 10. If the observed value of the signal plus noise is 12, just think about this. Now, this is a little crazy. I have Y is observed at 12. Y minus the noise is X. This is observed. Now this 12 is right dead center here. Y'all see that, class? That's observed, right? If you think about this, if that's observed, and that means that's where, when we add, remember, Y is observed, the randomness is going to be an X, but the randomness is really noise related. So it's going to be like this. The peak value is right there for f of X. Do y'all follow me? It has to be right there once we do the skewing and stuff. Because Y is observed, it means the statistics of f of X are going to be Gaussian. The only thing is the mean shifts to the center, because that's a constant. This is a constant right here. We don't have to do any integration. If it centers there, the most likely value would be 12. So part B would be 12. Y'all with me? All right, final question. And I'll put the math down in class. What happens if they say, repeat this of the observed value of 25? So what happens if we observe a value of 25? Just tell me, what's the most probable value for X if it's limited between 0 and 20? Anybody?
20.
You all see that? That's what the point he's trying to get across is, if it's a constant density function, whatever observed value is the most likely value for X because it's Gaussian noise. On either side of that, it's Gaussian. Y'all with me? Now, we'll go through the math in a little more detail, but that's it. And I'll do some more problems. I wanted to mention this, and before we end, and forgive me for any technical difficulties, I want to mention the next thing we're going to do is statistical independence. Now, it means one event is not in any way, shape, or form dependent on the other. And what that always means is that f of xy is simply f of xy times f of y of y. If you do the integration of f of xy, it has to equal this. Y'all with me? So if I mathematically give you f of xy, and you want to know if they're independent or statistically independent or not, if you go ahead and do the integration of that, f of xy with respect to x, and then you do it again with respect to y, so you get f of x and f of y. If you multiply those two things together and they're not equal to this, then it's not statistically independent. An example of something that is statistically independent of f of x is equal to a constant between 0 and 1. So it's 1. F of y is a constant between 0 and 1. All right. You go ahead and do this, you're going to find it works. Something that is not where there is dependency, if I have f of xy as a constant times x over y divided by y over that 0 to 1, 0 to 1, then it is not statistically independent, and we can prove that. You with me? So that's in a nutshell. Now, the only thing I'm going to ask you to do for Wednesday, to give me a little lead time in this, if you can read section 3.3, just go ahead, do the exercises. We're going to go through them right here. You're going to see some weird things happen here, and I'm going to go through this one here with the noise. I'm going to go through some problems. I'll give you a few problems on that. And I'm going to tell you the prior section 3-2 is a little confusing, but when we apply it for realistic problems, it'll sink in. It's not that hard to appreciate. But do these exercises and I'll give you some problems in the back. Then I'm going to say the last thing, because some people are thinking ahead to the quiz on Friday. I don't think I'm going to have time to quiz you on correlation, but I'm going to explain something about it in class on Wednesday if I have time. And I'm going to say that a lot of the stuff we're going to do with correlation is very valuable. it's very valuable in engineering, and you'll see this when you take, you haven't taken your communications courses yet, have you? You haven't taken, a Jatendra Tugnight's course communications, have you? Or not? You have? Campbell, you've already taken comm? No, I don't think you've taken communications. This is useful in communications, and it's the basis for information theory in some ways. Correlation tells you how much alike something is to something else. And whenever correlation is high, especially if one leads the other, you have a good chance of predicting or estimating the value of the other. That is so important in so many engineering things like failures, hitting a target. The stock market is where it's really important. I did a paper with another a undergrad, actually, a brilliant kid who got his PhD just recently from MIT, and this is a really smart guy, but we did it on using a genetic algorithm to predict stock market prices and then estimate the profit margin. It was scary, but this stuff's what we used, a lot of this, and we'll talk more about that later. I'm about done for today. I'm over. If you have any questions, let me know. Did y'all at least get something out of this besides we went over the test basically, right? Okay. Any questions at all? You guys are dismissed. If you
Wait, so are we having a quiz on Friday?
Yeah.
Okay, and what will that be on? You say yes?
What we covered today's stuff, the lecture, and it'll be on this in the next section. The homework I give today. How's that?
Okay, thanks.
Y'all with me? Please show up Wednesday. I don't know how many are down at the beach or where you are, but I hope you're having a good time and stay safe wherever you are. Anything else before I shut her down? I'll give you a quiz or your test back on Wednesday. Good deal? Well, thank you too. Have a great day. Stay safe. And I am going to give you some homework wherever you're at, so please do it. We'll talk about it on Wednesday. Okay. Are you seeing it now?
Yeah, I see it now.
All right.
So, I guess I had a question about maybe part A. I guess part C as well. I got negative of both those answers because when I did the integration, maybe I did it wrong. I ended up getting 1 equals A over 6, and then E times the negative that, and then you evaluate from. Huh?
I'll do it for you right here.
Okay, maybe I did it wrong. Maybe I just not very good at that integration, but
you can see the camera now, right? So you have f of xy equals a exp from minus 2x plus 3y, right?
Yeah.
And that's yx from 0 to, it's basically x greater than 0. That's the only thing you need. So that means if I do a double integral of xy, so I have put a out in front, and I have exp, and I'll put it to the minus 2x, right? And then times exp to the minus 3y, and I'm going dx dy from 0 to infinity, right?
Yeah.
And that has to be 1, right? So I'll just put 1 over a here, get rid of that. Now, if you look at this, when I integrate e to the minus 2x, what do I get? Dx.
It's just 1 over minus 2.
1 over what? Yeah, minus 2, right? And it's times exp from where? From exp to the minus 2x, and it's evaluated from 0 to infinity, right?
Yeah.
And then it's going to be, here it's going to be, when I do this, let's do this one here first. We'll do the other integral in a second. When I do this, I have minus 1/2. When I integrate this, e to the minus 2x from 0 to infinity, I can really say it's minus exp to the 0 minus, or and this would be plus exp to the minus infinity, right? Just do that one, you'll see it. You agree with that?
I guess so.
In other words, if you just forget about all this complication, if we just integrate simply e to the minus ax dx from 0 to infinity. You'll see it now. What do you end up getting? Minus
It's
1
just
over a.
it's just 0 minus 1 or
Yeah,
whatever.
Yeah, minus ax, and it's evaluated from 0 to 1, right? Or 0 to infinity.
Or it is 0 to infinity, but e to the negative infinity is just 0, and e to the 0 is just 1.
So it's going to be what? Minus 1 over a times 0 minus 1, right?
Yes.
That's 1 over a, isn't it?
Yeah.
All right. The negative sides cancel on that one.
So I guess my question is, if because you did it just one part there, you did
Both.
minus
you
1
want-
half
Yeah,
of
just
2x. So if you do,
go ahead. I mean, if you take a look at this, I'm just going to set it up. It's equal to
Okay.
the integral from 0 to infinity of exp to the minus 2x dx, right? And it's times the integral from 0 to infinity of exp to the minus 3y dy, right?
yeah, I think I see what I did actually.
So this is going to be a positive value. This is a positive value. They're both going to end up being, this is 1/2, this is 1/3. So this is going to be 1/6 is equal to a, or sorry, 1 over 6 is,
It's 1 over a.
it's 1 over a, my bad, 1 over a, my bad. Anyway, that's how you get it.
Okay, so you have to do the 0 minus 1, which is a -1 times a -1 because there's 2. So that just ends up being +1 times 1/6 is 1 over a. Okay.
Now, anytime you have f of xy can never be negative. That's another thing to always make sure you understand.
Okay.
I mean, you can't have an a there that's negative, or it's not a legal function. You can't have a negative probability.
Yeah, I think I evaluated it wrong for I only did one of the negatives, so I ended up getting a negative answer. Okay, that's cool. Thanks for going over that because I was
No problem.
confused.
I'm sorry, those are the things I know you can make irritating mistakes.
Yeah, it's all right. Thanks for going over that.